Good morning. So, I'm the new guy, and you may have noticed I like to use this dot cam, so that's what my fingernails look like. You're going to see a lot of those, I guess. So sorry about that. Somebody told me I need a manicure or something. So my name's Jason Harlow, and I'm going to be your physics teacher for the whole rest of the semester, up until the final exam. So some fun facts about me. I was a student here. I did a physics and astronomy specialist, graduated in '93. Then I went down, actually I took a year. I was a telescope operator at the David Dunlap Observatory in Richmond Hill, working basically as a technologist at U of T. And that's when I kind of realized I really wanted to know a lot more about astronomy, and I wanted to get my PhD. So I applied to various places, got accepted here and there, went to Penn State University, got my PhD down there, was looking at the faint end of the stellar luminosity function, studying stars mostly. And then I was actually in California. I lived there for 4 years as an assistant professor at the University of the Pacific in Stockton. Then I came back in 2004, and I've been a teaching faculty here ever since. More fun facts if you want to know. I did discover a star as an undergraduate. I don't know, it's sort of used to be my claim to fame, is that when I was undergraduate doing my fourth year research project in 1992-93, I was looking at the radial velocities of all these nearby stars. And one of them had a different velocity every night I would look at it. And I kept on looking at it and eventually realized it was two stars that had previously been thought to be one. And it wasn't until you looked at the Doppler shift of their spectral lines that you could see there was a second one. It took me, 3 years to write it up and get it published, but got a single author astronomical journal paper out of it. I'm also on Facebook and Twitter. I don't know what other fun facts you want to know about me, but you can always ask me, I guess. I think I might as well just get started. So Brian tells me you guys are done the first 7 chapters, so I was going to start in on chapter 8. So starts in on gravity. So we think of gravity as being the thing that pulls stuff down, right? Or if you roll off your bed, you fall off the bed and then hit the floor. So that's gravity. But what Isaac Newton realized is that gravity is actually an attractive force between any two masses. So me sitting here and you sitting there, we're attracted to each other by gravity, or any two people in this room, or any two objects. And so, let me turn down the brightness a little bit. And there's a law, there's a 1/r² law that Isaac Newton wrote down. The other thing I'll do is I'll change this to be, this is the force of mass 2 on mass 1. So put 2 on 1. And this is the force of 1 on 2. So just to be clear about that. And Newton's fourth law, or the law of gravity, is that F2 on 1 is the same as F1 on 2, and it's equal to capital G times M1 times M2 divided by R squared. And R is the distance between the centers of the two masses, and G is this universal gravitational constant, 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared. So it seems amazing. One of the reasons we don't notice stuff flying together, unless they're magnetic, is that universal gravitation constant is pretty small. 10 to the minus 11 in the sort of units of newtons. Even a newton is already pretty small. And so, like it's a tenth of a kilogram kind of thing. So 10 to the minus 11 newtons is really, really small. But you can measure it. We actually, if you go on to second year physics, and you take the PHY131H1F, one of the experiments you can choose is the Cavendish Experiment. It's a photograph of it, where you have these two lead balls, and they're on a pivot, and the pivot is held up by a torsion cable, and the torsion cable has a little mirror on it, and you shine a laser onto the mirror. And what happens is that as these little masses, actually there's two little masses inside the chamber where there's no air, and then there's two big masses outside. And what happens is the little masses oscillate back and forth, as they naturally do as they're swinging on the torsion. And what you do is you can switch the positions of the big lead balls. You can put them either in this configuration, 1-1, or in 2-2-2. And so if in 1-1, they both pull these things clockwise. If it's 2-2, these masses pull these balls counterclockwise. And it's a very small force. It's the gravitational force, but it's just measurable enough so that when you see the little laser dot on the wall across the room, you can measure that the center has shifted by a couple of millimeters, and then you do all your calculations, and you can measure what the G constant is. It takes about 2 weeks, and it's you're measuring 10 to the -8 newtons, so it's kind of hard to do, but it's doable. So, what does this have to do with us? Let's try to relate it back to what we've been doing for these first 7 chapters. Let's imagine that you have a mass, M1, this will be your little test mass. Maybe it's you, maybe it's this pen or something. M1 is the little thing. And then there's this giant spherical rock that's just floating in space. I don't know if you can imagine that, but this rock is 6 times 10 to the 24 kilograms in mass, and it has a radius of 6,400 kilometers. So it's a big thing, and it's a sphere. I don't know what it's like, but my question is, 2 questions. 1 is, what is the force of gravity on the little M1 due to the big giant spherical rock, M2? And then question B is going to be, let's think of a name for this, this rock. So let's first try it. So there's the center of M2, and remember, the center to center distance is what matters in this. We're going to compute A is going to be the force. We want to find the force of 2 on 1. Same equation for both. Is G times M1 times M2 divided by R squared. And remember, R is the distance between the centers of the 2 objects. Now M1 is very, very small, and it's sitting right at the edge of M2. So really, it should be the radius of M2 plus the radius of M1, but we're going to neglect the radius of M1 because it's so small, and say that R is approximately equal to this 6,400 kilometers. And I'll say times 10 to the 3 meters because I want to convert everything into SI units. Okay? And this is like the center to center distance. Okay, so now we can do that. I'm going to rearrange this a little bit. We don't actually know what M1 is, so I'm going to pull it out in front. It's M1 times 6.67 times 10 to the -11 newtons times, I think it's meters, squared, and kilograms to the -2. And then times this 6 times 10 to the 24 kilograms, and then divided by the 6,400 times 10 to the 3 squared. And I brought my calculator. So I got 6.67, not negative, 6.67 times...
Just a little bit off the screen to your left.
Oh, am I? Okay, thank you. Thanks, Kevin. Times 10 to the -11 times 6 exponent 24, and then divided by 6,400 exponent 3, and then squared. And it's equal to 9.77. And why don't we round that to 2 significant figures while we're at it? It's M1 times 9.8. That's kind of reminding me of something. And maybe it's actually going to help me answer part B, is what we're going to name this rock. We can also try to find what the units are. So there was a Newton up here. This was meters down here. I forgot to show you that. So the meters squared cancels the meter squared up here. Kilogram cancels one of these kilograms here. So what we end up with is newtons per kilogram. And by the way, this is a Newton per kilogram can be shown by the student to equal a meter per second squared. Kind of interesting fact. So this is, you times 9.8 meters per second squared times m1, and you'll get the force of gravity. Okay. So for B, I'm going to call this giant spherical rock floating in space Earth. So that's the joke. Thank you for laughing. That was good. All right. So this is where we get gravity for Earthlings. If you happen to live on the surface of a large planet with a radius r and mass m, then you can always write the gravitational force that you're going to usually feel as m times g, straight down. Okay? Where this quantity g is defined to be capital G, so lowercase g equals capital G, the universal constant, times the mass of whatever planet you happen to be on, divided by the radius of whatever planet you're on, squared. And so here on Earth, if you're at sea level, that's 9.83 to 3 significant figures. If you go up to the top of Mount Everest or something, it's not down to 9.71 meters per second squared, but it's some number. And the other thing that we can sometimes do is we can say that G with an arrow on it is down. It's the same magnitude as this, but it's down. So if you're on this planet here, then G will be in that direction there, or if you're in Australia, it's that direction there, which is why the Australians are all upside down, because gravity points towards the center of the planet. They think we're upside down, actually. Maybe they're right, I don't know. Okay. You guys doing okay? How's this doc cam working for you? Again, you're going to get tired of looking at my fingers. I'm going to have to paint my fingernails or something just now and again. Kind of spice things up a bit. Okay, so also going back in time and kind of looking at things, we've been doing a lot of projectile motion. And what we've been doing is we've been doing what's called the flat Earth approximation, which is that the gravity force is always down. And even if I move sideways, the gravity force is still pointing parallel to where it was before. So if I throw something, then it's got this constant y component of its acceleration always in the negative y direction. And we didn't think that changed. But in reality, and this is using the unfortunate notation W, W is weight. Anyway, it's the exact same thing as force of gravity. Those are synonymous. Okay. So this is your mg. It doesn't act down, it acts toward the center of the object. And so if you move far enough to the right, it'll eventually start turning. And so there's this idea that if you keep speeding things up, if the launch speed of the projectile is sufficiently large, there will come a point at which the curve of the trajectory and the curve of the Earth are kind of parallel. They're the same tangents. And it's just going to keep going and going and going. So if I take this marker and I really give it a good throw, and there wasn't a wall there and there was no air resistance, and I waited long enough, then boom, it would hit me in the back of the head eventually. About an hour and a half later, actually. So such a closed trajectory is called an orbit. Because if my head wasn't there, if I ducked, then it would just keep going, around and around and around, carried by its inertia, and it would never stop. Okay, so an orbiting projectile is in free fall. Same as any projectile is in free fall. There's only one force acting on it. It's the force of gravity. That's what we call free fall. If you're not in free fall, that means there's a normal force acting on your feet, right? So if you're ever in an elevator and there's a normal force acting on your feet, and then all of a sudden there's zero normal force acting on your feet, that goes to zero somehow, that means you're in free fall. And that's not good. It means you're accelerating downwards at 9.8 meters per second squared, right? So be wary of that. So the thing I want to do, there's this learning catalytics stuff, right? Brian's here to help me in case I start panicking. I got a lot of questions about this in the pre-class quiz. So this is a picture of a guy, and this guy is currently, right now, in space. His name's Randy Bresnik. He also is on Twitter, by the way, you can follow him. He actually frequently posts stuff like pictures he took of Greenland going by or something like that. Cool guy. He's 370 kilometers above the surface of the Earth. Now, he's not on a diet, but he can measure the force of gravity on himself somehow, or maybe he knows it. So my question is, what is the force of gravity on Randy compared to what it was before when he was here on Earth? Is it gone to A, 0, B, the same as the force of gravity on him while he was on Earth, C, a little bit less than the force of gravity on him while he was on Earth, D, not exactly 0, but much, much less than the force of gravity on him while he was on Earth? So think about that. Try to choose an answer on your phone, hoping that's working for you. And then I'd like you to pair up and discuss with your neighbor and make sure your neighbor voted the same way. Okay. Whoop. Okay. Now I have a cough drop, so sorry about coughing earlier. So I'm going to show the results on your phone, I guess. Whoop. And circle it. It's actually C. A little bit less than the force of gravity on him was while he was on Earth. So I'll try to explain that with this diagram, which is drawn to scale. So the radius of the Earth is 6,400 kilometers. And the altitude of the International Space Station is 370 kilometers. That's not very high, really, compared to the radius of the Earth. Okay, so if you take R, for us right now, distance from us to the center of the Earth, that's 6,400 kilometers. If you take it for Randy, it's going to be 6,770, something like that. A little bit more, and so there is a reduction. He's now feeling that little g of 8.9 meters per second squared. Okay. But almost the same force of gravity is acting on him. But he still feels weightless, and this is a picture of him trying to have a snack, which is hard to do when you're feeling weightless because you have to squirt your chocolate sauce onto some sort of little waffle or something like that. But the reason is, for him, the reason he feels weightless is the same exact reason that you feel weightless when you're in an elevator that's falling down at 9.8. He is accelerating towards the center of the Earth at 8.9 meters per second squared. The whole space station is. But it doesn't get any closer to the Earth because as it's accelerating towards the center, it's also moving sideways. This is an example of uniform circular motion. And uniform circular motion has an acceleration. Do you guys remember what it is? It's v squared over r. Thank you. So that's what this 8.9 meters per second squared is for Randy. It's v squared over r. V is so high for him, this sideways motion, that it's exactly compensated for by gravity. He's just falling and falling, but never hitting. Okay. Where am I? So here's a fun little example we can try. How fast would you have to drive in order for the normal force on the bottom of your car to go to 0? So what I want you to imagine now is you're driving on the surface of the Earth. And here's your car. A little hard to see here. This is the Earth. Your car is going this way at speed v. And then what's happening is that there's an acceleration towards the center, one we call a sub c. A sub c is equal to v squared over r. Okay, where r is equal to 6,400 times 10 to the 3 meters. Okay, so we can draw a free body diagram of the car. And all the forces that are acting on it. So you've got mg acting downwards, as you always do if you're near the surface of a planet. What else? Yeah, that's right, we're done. The silence was exactly correct. So the normal force is equal to 0. That's what we've set it at for the car to feel weightless. Feeling weightless means when you stand on the scale, it reads 0. You have 0 weight, as measured by the scale, I guess. It's sort of an apparent feeling. Anyway, so the F net on this car, which is just equal to mg, all the forces down. And that is going to equal to the mass times the acceleration. So it's the mass times v squared over r. And then the masses cancel. Doesn't matter what the mass is. You end up with g times r equals v squared. You can rearrange that to be v is equal to the square root of g times r is equal to the square root of 9.8 times 6,400 times 10 to the 3. Sorry for your handwriting that on the screen. So it's square root, open parenthesis, 9.8 times 6,400, exponent 3, and parenthesis. And it's some huge number. It's 7919.6, and that's going to be meters per second. Okay? And you can, it's, you know, you can convert it to kilometers. You can go 7.9 kilometers per second. So this is really fast. Remember, that's, so actually you can divide by 1,000 if you want to convert to kilometers per second. Then you can times it by 3,600 if you want to convert it to kilometers per hour. It's actually 28,000 kilometers per hour. So you're speeding. Okay. You guys are so easy to make laugh. It's really good. I feel like a stand-up routine or something. Okay, so circular orbits is basically this radial acceleration, also called centripetal acceleration, v squared over r equals g. Okay, another way of saying that is that the force of gravity is the net force on you, and the net force on you is mg, but the m's cancel. That is your v orbit is the square root of rg, and near the surface of the Earth, this is about 8 kilometers per second, as we just proved. Okay, and an object with any other speed will not follow a circular orbit. So we'll talk about what happens if you're at other speeds. If you're slower than that, then you're going to crash into the Earth. If you're going faster than that, then it'll no longer be a circular orbit. But it still might be a closed orbit. So now I want to do the next question. So what do? I press this thingy? Do I have to undeliver the other one?
No. Just hit the right arrow. Just go to 2.
Okay.
Or that one, yeah.
Mm-hmm. And just press deliver? Okay. And it's not paused. Okay, good. Okay, so here's my question. It's not cheap to put things up into space. Okay, and you would think all you'd have to do is just go at this 8 kilometers per second if you want to orbit the Earth. So saying that we want to orbit the Earth, why do you have to launch it up to this 370 kilometers, for example? Show all the results, and I will circle the one that I think is the answer. So I don't know what you guys thought I was asking here, but the basic idea is that if you drive your car at 8 kilometers per second, you and the car will be instantly vaporized by air resistance. And you just can't do it. It's too much air to plow through. So the reason we go to 370 kilometers above the surface of Earth is because there's no air there. so there's no air resistance. So if you're already going 8 kilometers per second, you can just keep going forever and ever. You don't have to have any rockets, except the ones that got you there in the first place. You just go by inertia after that. Okay. Now that's not exactly true. There is a little bit of air out there. Even in the interstellar medium, there are particles. And so it does get slowed down a little bit. And so they do have little boosters. And if you leave a satellite up in low Earth orbit for enough time, 20 years or something, its orbit will start to decay exponentially as it gets lower and lower. It encounters more and more air resistance, and it eventually actually will hit the Earth and burn up as it's falling down. Okay. So we're kind of moving right along here. This is getting into an astronomy history lesson now at some point. So this is long, long ago, even before Isaac Newton. A lot of people consider the first sort of real scientist using the scientific method to be Galileo Galilei, an Italian guy who had a telescope. He wasn't the first person to have a telescope. There were people using telescopes for sailing and looking sideways at other people, usually the enemy. But he took the same telescope and he pointed it up and said, hey, what's all those stars I used to see? And what he saw was some really interesting stuff. Those points of light that you see as stars are still just points of light, except for 5 of them, which is Mercury, Venus, Mars, and Jupiter and Saturn. Those moving stars, they all turned out that he could actually see a little disk. And with Saturn, he could even see these little rings, and he was really freaking out because he felt that this meant something. And it does mean something. What it means is that those planets are much closer to us, so we can actually see them with a little telescope. We can see like a picture of them in your telescope. And then there were other people that didn't really have telescopes, but were looking at those same planets and very carefully mapping their position against the background of stars and trying to figure out what the planets were doing. And it was Kepler that analyzed a whole bunch of data of careful observations of the apparent positions of planets, and he came up with these Kepler's laws. And the Kepler's laws they didn't really come from any theories or anything, they just came from his observations. And in fact, the going theory of the time, what Kepler was hired to prove, is that all the planets were actually orbiting the sun in perfectly circular paths. And unfortunately, the first thing he had to tell his boss is that, well, I have proved that they're definitely not moving in perfectly circular paths. And so, but he wasn't fired, he continued on, because there was another mathematical shape called an ellipse. I don't know if we want to do it. Want to do it? It's that same thing that you do when you draw an ellipse. I can press the focus button or something. So, what do we got here? Got some tacks, got a piece of string. So all you do is you draw an ellipse, is you have to put 2 tacks in a piece of paper, and you take a loop of string and wrap it around the 2 tacks. And then you take your pen and I guess we can put the knot in between there, and you stretch it out to make a triangle. And then you just go around all the way. It's lots of fun to do at parties. You get to the end, and that's a perfect ellipse. And so what's happening is that for every point on this line, the sum of the distance from the blue tack and the distance from the red tack is some fixed number. And so then you take away your string, throw it over there, take out your tacks, and you look at it, and you see that, okay, well, there's 2 tack marks. We can draw a line through the 2 tack marks. Okay. We call this the major axis. You can find the halfway point between the tack marks and go on a perpendicular. And this is what's called the minor axis. And what Kepler found is that the sun is one of the 2 tacks, and the paths of all these planets are elliptical. Oop, going off the bottom of the screen here. But so sometimes the planets are close to the sun, sometimes the planets are a little further away. Now, it was very difficult for him to figure this out because the planets' actual orbits are not this squishy of an ellipse, they're much more circular. And in fact, just to emphasize this point, it turns out that for the Earth, the perihelion, where it's closest to the sun, happens around January 4th. And when it's furthest from the sun, happens around July 4th. And so, it may seem a little strange, right? Because it's so much warmer in July when we're actually furthest from the sun than it is in January when we're actually closest to the sun. And so the seasons of winter and summer are not caused by this. They're caused by something else. They're caused by the tilt of the Earth. And this effect is actually only like a little bit of a 5% effect. We're only like 5% closer in January than we are in July. So, but maybe it makes the Australian summers even a little bit warmer. Okay. So there's a mathematical equation for it. Kepler was a mathematician, so we knew all this stuff. There was even an equation, x squared plus y squared. So what that's doing is that's setting the y-axis to be here and the x-axis to be here. And A is now the semi-major axis, half the major axis, and B is the semi-minor axis. There's something called the eccentricity, or the squishiness of it, which is this distance c divided by A. And a circle is a special case of an ellipse. So it is certainly possible for a planet to have a circular orbit, because a circle is a special case of an ellipse. So we're still okay in terms of our physics. And where this all comes up is in Kepler's first law, which is that anything that orbits the sun has an orbital path whose shape is an ellipse, with the sun at one focus. And there was a lot of concern on the pre-class quiz this morning about what is at the other focus. And because my answer is that there's nothing at the other focus. If the sun's at the red tack, there's just empty space over at the blue tack. It's just a mathematical point, which doesn't have any physical significance. Okay, number 2 is that a line drawn between the sun and the planet sweeps out equal areas during equal intervals of time. So again, Kepler was looking at one planet and seeing that it seemed to go faster when it was closer to the sun than further away. And being a mathematician, he put this into terms of math. He said that if this is the sun, and this is the planet going, let's say, this way, I guess, then this line drawn sweeps out some area over some time. Okay, so this would be the area of this weird shape over some time to go from here to here. Then, to go from here to here, if it's the same area, this is a sort of a triangle that's a lot taller, it goes a shorter distance. So what this means just is a mathy way of saying it goes slow when it's far from the sun, and it goes faster when it's closer to the sun. And then the third one, he had to look at lots of different planets. He found that the orbital period of planets is longer the further they are away. Okay. And then what came from this is actually, these were just, I guess, empirical laws. I'll scan all these things after the class and post them up. Kepler's laws are empirical, like Hooke's law, which was Hooke measured that there is this force that's proportional to distance of a spring, but he didn't really know why. Same thing with Kepler's law. He measured these things happening and just said what he measured in a mathematical way, which isn't exactly the same as a more theoretical law where you kind of start with the reasons and then create your equations. You can see the difference. He did not know why the planets moved in this way. Now, there were lots of scientists that believed that there must be some kind of force coming from the sun that would keep these planets doing this elliptical thing in just the way as shown by Kepler's laws. But no one could really figure it out. And the reason was because we didn't have calculus. So Isaac Newton, who was doing lots of things, was a very mathematical guy. looked at this and thought, yeah, maybe this could be solved, but you would have to invent calculus, and he didn't want to do it. But Edmund Halley, who discovered Halley's comet, kept on knocking on his door again and again, saying, please do it, like none of us can figure this out, and just kept on bugging him, so that Newton, just to get these guys to go away, invented calculus, derived all of Kepler's laws based on some very, basically Newton's 3 laws of motion plus this law of gravity, and then they went away and left him alone. And actually, 95% of what Isaac Newton did write about was these theological sort of analyses of the Bible. He was very, very deeply religious and really was thinking about the Bible a lot. And this is, in his spare time, he did all his math and physics work. So, kind of strange. What time are we at here? Getting towards the end. So, these parabolic trajectories of projectiles near Earth's surface are actually portions of ellipses. When you look closely enough at an elliptical path, it starts to look like a parabola, and that is that flat Earth approximation. So when I throw this pen up in the air and it does that thing, if it didn't hit the ground, it would continue in that path and trace out a very, very eccentric ellipse. It would go around the center and then come back up. It would go a lot faster once it got to the center. Now, of course, it hits the Earth, so it's a little more complicated than that, but what else? I guess I want to talk a little bit about gravitational potential energy. Now, we had MGH before. When you're looking at large distances, two masses M1, M2, destroyed that pen somehow by throwing it around, I guess, right? Don't throw your pen around when the lid is off, or you wreck your Sharpie. Gravitational potential energy that's formed by two masses, M1 and M2, is equal to a negative G times M1 times M2 divided by R, where we have chosen the 0 point of potential energy out at R equals infinity. So if you take two masses and separate them very, very far away from each other, R is very large. It's on the denominator of this equation, so U goes to 0. And then what we say is as they get closer together, it's weird because they get more and more negative. They lose gravitational potential energy as they get closer together, right? Because they're speeding up. Same way as if something's falling, it's losing its gravitational potential energy, the U bar is going down, and the kinetic energy bar is going up. Well, it looks like as R goes down, this thing should go up. But remember, the whole thing is negative. So as this quantity goes up, it's getting more and more negative. So it's losing potential energy. And if you look at orbits, so U is always negative, remember that. Kinetic energy is always positive. If you add the kinetic energy plus the potential energy, you get what type of orbit it is. This is the total mechanical energy. If the total mechanical energy is less than 0, by this 0 point definition that we have for potential energy, that's what's called a bound orbit. Okay, so out at infinity, it can't get to infinity. It's always stuck at Earth. And then special cases would be circular orbits and just falling objects. I dropped this pen, it's got total energy is negative. If E is greater than 0, that means that out at infinity it can still be moving, which means that it can escape. And E equals 0 is this borderline where you just have enough energy to escape. And the figure from Wolfson looks like this. Here you plotted gravitational potential energy, which looks like this curved line. And here is the total energy. If the total energy is less than 0, then the maximum distance that the two objects can be from each other is R1. Okay. If the energy goes up, then it can get further and further up. But if it goes all the way up to 0, then it never comes back down again. It just keeps on going. And these are called open orbits, where it can go forever and have positive kinetic energy. And what those look like in real life, sort of side view there, is all these are closed orbits with E less than 0. And then this one is the borderline. This is E equals 0. And the open is E greater than 0. Okay. So, I think I want to do this one. A little bit of time. There is a saying that what goes up must come down. Is this always true? And I'm going to do a little example. When the total energy equals 0, then as r approaches infinity, k will approach 0. This is the escape speed. So I kind of want to do that just to show you. So if we do k plus u equals 0, the kinetic energy is 1/2 mv squared. And we'll do a minus g times m times the mass of the Earth divided by the radius of the Earth, okay, equals 0. Now, some things are going to cancel. This little m will cancel on both sides. We can pull this over to the other side, and we get that g times the mass of the Earth divided by radius of the Earth is equal to v squared over 2. We can solve that out and say that v is equal to square root of 2 times g times mass of the Earth over the radius of the Earth, not squared. And I'm not going to throw my calculator up there, but it turns out that this is equal to 11 kilometers per second. And this is called v escape. So it's bigger than the circular orbit velocity. So if you're going 8 kilometers per second, you can orbit the Earth without hitting it. If you go 11 kilometers per second, basically in any direction, or if I throw this pen upwards at 11 kilometers per second or greater, and there's no air resistance, then it never comes back down. It just keeps going. That's the escape velocity. And the other thing I would notice here is that as the radius of the Earth goes down, the v escape goes up. And I think there is some limit where if you get less and less and less, smaller and smaller, if the Earth's radius was less than 9 millimeters, which is kind of small, then the escape speed, v, would end up being greater than 300,000 kilometers per second. And the reason that's important is because it's impossible in physics for anything to go 300,000 kilometers per second. It's against the laws of Einstein's relativity, because that's the speed of light, can't go faster than light. So, if the Earth was compact enough and smaller than 9 millimeters, but had the same mass, it would be impossible for anything to escape it. Anything that got close enough to it, would get sucked in and could not physically escape. And so it would be called a black hole. That's all a black hole is. It's just a small thing. Okay. Small and massive thing. All right, I'm kind of running out of time here. So we're not going to do another Learning Catalytics question. But before class 14 on Monday, remember that over the weekend you should do this homework 6 on chapter 7, which is due Monday evening. You should read the first 2 sections of chapter 9 on center of mass and conservation of momentum, and or you can watch my pre-class 14 video. And there's a little, if you scan the code, you just see that video. And something to think about over the weekend, how is it possible to clear the bar in a high jump without your actual center of mass clearing the bar? There's a way to do it, and I'll talk about that more on Monday. It was good to meet you, and have a good weekend. Thank you.